Welcome to the Water Resources Podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the University of Texas at Austin. This podcast is produced in partnership with the National Academy of Engineering. In this podcast, we discuss water challenges with leading experts. It's my pleasure to welcome Dr. Allan MacDonald to the podcast. Allan is the Head of Groundwater at the British Geological Survey and is stationed in Edinburgh. And his focus mostly is on groundwater development and management in developing countries for poverty reduction and water security. He's worked in many different countries, particularly Africa, India, but also in the UK. And today we're going to talk about much of this work. So Allan, I think I would like to start with your recent work on northwest India and central Pakistan, which was really surprising and interesting, your findings. We've been hearing so much about satellite data and depletion in that region from the grey satellite data over the past couple of decades. And your work has shed some light onto long-term development in this region. So could you describe a little bit about that and your collaboration with the Donald McAllister?
Thanks very much, Bridget, and it's lovely to be here chatting with you. So this is work we just published this year, and it was led by Donald John McAllister and in collaboration with the National Institute of Hydrology in India and in Pakistan. With some scientists there. And what we were trying to do was put the recent trends from GRACE, the last 20 years depletion that you get in that region, trying to put that in a much longer context. So GRACE has been fantastic, as you know, in uncovering what's happening at the moment over these kind of large footprints. But we thought, well, let's look back a little bit more into the past. So what we had done is over about 3 years, sort of painstakingly put together lots of old borehole records of groundwater levels from not just this century, but going back throughout the whole of the 20th century and even back into the 19th century, the latter half of the 19th century. And what we discovered was that the big story for this area is really one of groundwater accumulation, not depletion. So groundwater levels have been rising there mostly since the 1850s. They've been rising until the end of the 20th century, when they're now beginning to fall with all the rapid abstraction. So that was our big findings, really, and was really good to get all that data out there for other people to look at and to use.
And why were the groundwater levels rising? I mean, the British, under British rule, you had a lot of canal irrigation. And so you had to reconstruct a lot of those data from old reports and stuff. So maybe you can explain a little bit about that connection between surface water and groundwater and.
So that's really the reason why groundwater levels have changed so much. It's human intervention. So in this area, it was a huge building of canals that began in the latter half of the 19th century. I mean, there had been canals in this area actually for thousands of years, sort of small irrigated canals. There was a really, thriving agricultural economy there for thousands of years. But it was during the middle half of the 19th century that began this sort of mass construction of large canals, which continued throughout the 20th century. And these are huge canals. I mean, like me, if you're in the UK, you're used to seeing canals in our cities, which are fairly small things, but these canals are a much bigger scale. And what's happened really is that these canals have been leaking water into the groundwater system. So over the last century, the surface water was being distributed out onto the interflows, and the water was recharging through the fields and the small canals into the groundwater. And gradually they were just, the groundwater levels were increasing. And some places you were then getting problems with salinization and people had to put in drains to try and get rid of the excess water. So that was really why groundwater accumulated. And what we had done was, as you say, is put together all these old records to try and find the kind of scale of it. And I suppose that's what maybe surprised us, is that at a minimum, the amount of water that's accumulated is about 4 to 5 times what's been depleted in the last 20 years. We've actually got 4 or 5 times that actually accumulated during the 20th century. So it was the canals. And another interesting aspect of that was that groundwater levels were rising even when the climate was really dry. So over decades in the 20th century, when it was really dry, you actually got groundwater levels rising as a result of the canal leakage.
And I think that's really important because people forget sometimes about this connection between surface water and groundwater. And oftentimes you hear of groups saying they want to line the canals and make them more efficient and stop the leakage, not recognizing that that leakage is actually feeding another system, and it is not a true loss to the entire system when you consider groundwater and surface water together.
Yeah, I completely agree. We sometimes think of them as separate resources, and they're definitely not. They're so interlinked in terms of groundwater recharge or base flow to rivers. So we need to treat them as one. So by lining the canals, it might stop one problem, but it really starts another one for the groundwater system. So it might be good to line them if you're over a really saline aquifer where the water would just go to complete waste. But when it's over an aquifer that is of good quality, then actually the leakage has been fantastic at being extra storage really for the groundwater system.
And then could later come out in the surface water as base flow in the rivers.
You've got base flow or what happens very much in this region in northern India and into Pakistan is that later on in the 20th century, when drilling became a lot cheaper and much more widespread, farmers realized that actually if you drill your own borehole and get groundwater, you've got a lot more control. You could, you don't have to wait for the surface water to come down the irrigation canal. This was particularly important for people who were down the end of a canal system that often didn't get as much water as they wanted. So hence you got this big explosion in groundwater drilling, and across the Indo-Gangetic Basin aquifer, which is a big long name for this whole region, there's about 10 million boreholes. So there's a lot of boreholes. So that gave the farmers the control that they wanted for when they could pump out, and led to more cropping. So sometimes you now get 3 crops in a year because they're able to access this groundwater storage.
And how deep are these wells, or are they deepening over time? Or did they start off very shallow and then now they're getting deeper and deeper?
Yeah, that's a good question. And to start off with, the boreholes are pretty shallow because this is a kind of alluvial plain, so the groundwater is pretty close to the surface, and certainly now that the water levels have risen so much. So boreholes could be quite shallow, 20, 30 meters to access groundwater. But now, you're looking at 50 or 100 meters boreholes being pumped, and if people can, they're drilling deeper ones to give them that security. Because in this huge alluvial plain, the sediments can be hundreds, up to a kilometer, even more than a kilometer thick up in the northwest of India and Pakistan. They're really thick sediments, a thick aquifer.
So, I mean, the recharge that you got from the canals, from the mid 1800s to, late 1900s, that's kind of like a giant managed aquifer recharge project. We talk a lot about managed aquifer recharge these days, where we take maybe excess surface water and put it in groundwater. But that really is a similar behavior and it was probably the biggest in the world.
Yeah, that's what we like to say, that this was the biggest, albeit an accidental one, but the biggest managed aquifer recharge system in the world, and really it has really given this big increase of groundwater from surface water. So transferred that surface water, the excess surface water, into the groundwater system. And there was a discussion in the 1970s about trying to make use of that behavior. They called it the Ganges water machine. So two scientists had proposed that actually we deliberately lower groundwater levels next to the Ganges during the the dry season, so that when the wet season came, then it could capture more of the floodwater as it came down. So these were put forward as a very expensive but serious proposal to try and make use of this and try and enhance it. And they actually, the World Bank were looking at this again recently, and there was some papers out by Cliff Voss and others looking at this in the last sort of 10 years or so, to say, well, actually, let's think about this again. Could this actually be done? Could we transfer some of this floodwater into the groundwater system?
Well, I think, that's one of the challenges we're facing these days, because we either have too much water when it's flooding or no water when it's during drought. And so it's trying to manage those extremes. And so understanding the linkages then between surface water and groundwater and managing it accordingly. I think in the US, the Army Corps of Engineers is trying to manage their reservoirs somewhat like that. They call it forecast-informed reservoir operations. So if they're expecting a flood, then they would offload the water to a nearby depleted aquifer or some interim storage. And then they'd have more space then for the flood water and could capture more of it. So I think we have to get more ingenious about how we manage these systems when we're trying to deal with these challenging times. A lot of us, focus on water quantity issues, but I mean, water quality is also a big issue. And what is the water quality like in this part of the basin, and how is it changing, or so what do you think the future is also for water quality issues?
Yeah, well, water quality is a massive issue, and we'd written a paper with National Institute of Hydrology and a lot of other partners on the groundwater quality, endocongetic phase and aquifer back in 2016, where we kind of concluded that we thought water quality would be a bigger issue than depletion. And the GRACE satellites have been fantastic at highlighting the depletion, but we thought, actually, let's look again at the water quality. A lot of people remember or know that when you go down towards Bangladesh, you have a big problem with arsenic in the groundwater system. There's been lots of work done on that, looking at the very high arsenic in the shallow groundwater systems. But you also get water quality as you go further up the basin into northwest India and into the top of the Indus in Pakistan. And part of that is arsenic. Not as much as further down the system, and that's because of the age of the sediments. Very young sediments that are deposited in this basin tend to have arsenic, the high arsenic contamination associated with them. You also get issues with fluoride, some issues with uranium. I mean, it's sounding bad, but this is not all over the place. And if you do some proper sampling and analysis, you can work out if you're how bad the water is. But generally, it's of pretty good quality. You just got to watch out for these patches with arsenic, fluoride, and uranium. But probably what I think might be the threat here is increased salinity. So as you have the flooding and shallow groundwater levels, then you get a lot of evaporation, and you can get quite saline groundwater close to the surface. So managing this aquifer system to make sure that you don't have a lot of shallow groundwater giving rise to high salinity, I think is going to be one of the big challenges. Managing that kind of flooding next to the depletion. So trying to manage both of these things at the same time, I think, is going to be one of the big challenges.
And, in general, in many places, the shallow groundwater is oftentimes more contaminated than the deeper groundwater. And so as you see groundwater developing deeper and deeper, do you think that may cause increased contamination, moving down into the system? Or
yeah, that's a good question, and a really important one for thinking of the long-term protection of this groundwater as well. Can we protect parts of it that don't get contaminated? So yeah, parts of the shallow groundwater system are contaminated by the normal stuff, fertilizers and nitrate, and also with your kind of organic contaminants that we get from pharmaceuticals and pesticides that we find most places, where there's humans. So you get some contamination in the shallow system of that. So when you develop deeper, then that pumping can begin to induce some vertical flows through the aquifer. And that's something we've been doing quite a bit of research on recently. It's trying to look at how connected these shallow and deep systems are. Because if you go right down the basin to Bangladesh, where all the arsenic is in the shallow system, you actually find the deeper groundwater there is quite disconnected most of the time. There's a lot of clay layers and a lot of clay layers in the system, and that kind of gives some protection. But up at the top of the basin, so North India and Pakistan, it's a much more,
That's me.
Up the top of the basin, then there's not so much clay. So what we found is that by pumping deeper, that we are finding that the shallow groundwater can go down into the deeper system. So that's something to look out for, that the deeper groundwater might be a little bit more vulnerable to contamination than it is further down the basin.
So what has been the response of the Indian government to your recent studies then showing that you have a net accumulation of, you know, so much water, groundwater over the past century? What has been their response to these results?
Well, we've been very fortunate in this study in having the National Institute of Hydrology, who's a government agency, as part of the study, and also being with being in contact with the Central Groundwater Board there as well. So they do a lot, particularly Central Groundwater Board, in trying to manage groundwater across northern India. So I think the accumulation is really interesting, and I think what it's telling them and us is that we're still getting a lot of groundwater recharge from canals. So, you know, the canals are still there and they're still leaking. We might not see the huge accumulation just now because they're pumping and the groundwater levels are going down, but it's trying to take into consideration the fact that these canals are still part of the system, and to think once, think twice about lining these canals everywhere, because they're part of the groundwater recharge story. And I think some of the challenges that they're also grappling with is how to try and manage both accumulation and salinity and depletion in the same breath, particularly when you've now got the possibility of solar pumps. So maybe there might be more groundwater abstraction happening in the future. So trying to manage that.
And so managing the surface water and groundwater conjunctively then, I think, would be really important to develop more resilience in the system as they go forward. But probably different government agencies in charge of surface water and groundwater and different agencies in charge of agricultural development. So it's very difficult, it seems, to coordinate.
It's very difficult for them, and it's very difficult for most countries in the world. We seem to have made it really difficult for ourselves to try and manage our water resources by having such distributed or disconnected institutes trying to manage water resources. So yes, you've got the agricultural bodies, and you've also got, as you have in the US, they've got the states and the federal system. So trying to balance all these things and the inputs and outputs. What's been great in India has been they've been publishing a lot more data. So as technology gets better, so a lot of data is now more widely available, and they've got lots of forecasts that they publish every year about whether groundwater is being overexploited or not. So hopefully that's giving the tools to try and help manage things conjunctively in the future.
Well, I really commend you guys for sleuthing through all those data reports and everything, and reconstructing the canal development and the groundwater levels from old reports and everything, and showing the increase in tube wells that were installed in the late 1900s and stuff. I mean, it's just. Those records and those reports are very vulnerable to being destroyed or lost, and so pulling all those data together is extremely valuable, because you can't replace them. You can't generate that after the fact. You can probably model it, but I mean, I admire you guys for doing all of that.
Thank you. I seem to have done that for most of my career. is what I do is I love to go through it and rummage through filing cabinets in people's offices, because often people don't have the time to look at data and to to do something with it. So I love just going through and seeing what I can find, and then seeing if we can make that more useful to them, or to and to everybody else. So yeah, as you say, these data are so precious and so vulnerable.
And I think we feel these days, unless it's online, it doesn't exist.
Yeah, that's
and,
right.
so, and so I think it's very important that we don't go that route. So now jumping to another area, to Africa, where you have spent a lot of your career and made huge advances. And I think maybe starting with the paper that you published in Environmental Research Letters in 2012, that had a huge impact on people's perception and understanding of groundwater resources in Africa. Maybe you can describe a little bit about that work, and then what the feedback was from the community and from other groups, as they learn more about the system.
Oh, yeah, certainly. So this was, some work that we published in 2012, and again, it had taken us several years of just going through different data reports and maps with partners. And what we were trying to do was give a quantification of the available groundwater resources across Africa and how they could be exploited. So what kind of yields you'd get if you would drill a well somewhere. And it was at a continental scale. So not for somebody to go out and site a well in a particular village, but just to give this view to help donors and UN agencies think about using groundwater as a resource to help improve climate resilience. So that was the reason behind it all. So we ended up publishing some maps in 2012, and it went viral. It went my life changed for about 6 months after that. So it was some work that the numbers got picked up by the BBC and went all around the world for a number of months. And really, I think what interested people probably wasn't a surprise to most hydrogeologists, but seemed to be a surprise to a lot of other people, was that there's 100 times more groundwater resources than there were annual renewable surface water resources. So that was our kind of headline figure. It just showed just a great potential that groundwater has as nature's reservoir. So there was lots of media interest in it, and then that gave opportunity for a lot of my people that I worked with, my collaborators and partners in different African countries, to just suddenly explain to their ministers what's all this groundwater resources. And so it kind of gave groundwater a little bit more of a visibility across many of these countries. I think what a lot of the newspapers began to concentrate on was the big groundwater resources under the Sahara. That's what everybody's always interested in, or seems to be interested in. These great untapped lakes of groundwater under the Sahara Desert. But that wasn't really my main interest, and most of the people that were working on it wasn't really our interest. It was more the groundwater resources available where people lived, and particularly in the crystalline basement aquifers, which are the hard rocks, the granites and the gneisses, these big crystalline rocks, which we normally don't think of a lot of groundwater in them. But when they weather, when they've got tropical weathering, then maybe the top 50 meters are slightly broken. There's maybe turned into sands and gravels, or are more fractured. And then you can actually drill boreholes, and you can get enough water for a community water supply with a hand pump, or maybe small scale irrigation. So that was really most of our interest was in that, rather than the huge sandstone aquifers, the Nubian aquifers and such that are in the North Africa.
So the Nubian and some of those northern African aquifers are probably more similar to the Indo-Gangetic Basin, kilometers thick, but very low rates of replenishment, low recharge rates. And so, you know, there's a lot of irrigation in North Africa, and so maybe they've been declining some. But the basement aquifers and the weathered basement is probably more prevalent in maybe 40% of the continent.
Yeah.
And so these are fairly thin aquifers then. And, you know, a lot of people are concerned about over-exploiting aquifers. But, I mean, these relatively thin aquifers, I mean, they're sort of self-regulated, right? I mean, you can't go too far wrong and because it's a dynamic system.
Yeah. So the basement aquifers, they've got quite low permeability. So when you pump them, it's hard for you to pump out the whole of the abstract the whole aquifer. It's not like you can drill one well and you're going to be affecting people tens of kilometers away. It's got a smaller cone of depression, so it's quite hard to pump out a high yield from an individual borehole. It can be done, and we've done quite a bit of work with Richard Taylor and others looking at where you might get high yielding boreholes in crystalline basement, but it's pretty rare. So the majority of people and majority of places, it's hard to pump out too much. And on the kind of sustainability side of it, the 2012 maps, we hadn't considered groundwater recharge at that point. So we started another project with Mike Edmonds, who's sadly not with us any longer. We started working with him, getting together a data set of groundwater recharge then across Africa, of course, which you were involved in as well, Bridget. So that was really useful, having that added story. We published that just last year, which showed the patterns of groundwater recharge across Africa. And for most of the crystalline basement aquifers, which are these low storage ones, as you say, most of them are actually in areas where you do get regular recharge. They're more in the subtropical areas where you get regular recharge. So it's unlikely that you're going to get multiple years of drought to dry them out. And as you say, the big sandstone aquifers, which are the huge groundwater storage, particularly in North Africa, they're the ones where you don't get a lot of recharge. But you've got this amazing groundwater storage, which people are using, as you say, to irrigate and for drinking water at the moment.
And so I think, you know, with these maps then, I mean, you show the importance of the geology and understanding the geology. And oftentimes these days, you know, we do everything desktop and things like that. But going out into the field and then taking advantage of all the mapping that the different agencies did back in the 1900s. I mean, the British, the French, and all of that, and all those reports. I mean, they're a huge resource to understand these systems. And I think one thing that comes to mind is, you know, the difficulty of drilling a successful well in some of these basement aquifers, you know, when you're trying to find fractures and stuff, and you have to use other tools to try to drill more successful wells.
Yeah. It's quite a lot of pressure on a driller to try and find groundwater in a village. You know, you have these big water projects, and you know, having to go out to a village and find a place where you actually can drill a successful borehole. I mean, in some places like the Indo-Gangetic Basin, you could drill most places and you'll find enough water for a hand pump. But in the crystalline basement aquifers, you've got to find the places where the fractures are, where the regolith is deep enough. So, I mean, two things are important there. One is experience. So having drillers and hydrogeologists that know their area, know it well, and then using geophysics as well. So geophysics has been a great tool for siting boreholes in basement aquifers, trying to find areas that conduct electricity a little bit more, a little bit easier, tends to mean it's got thicker weathering and therefore a better target. But drilling a borehole is always a lottery. You know, you can minimize the odds or get the odds more in your favor, but you can never say it's going to be 100% successful. That's something that I try and do with my work with donors or with people who are funding projects, is not to put too much unrealistic expectations. You're not going to get 100% success rate. So make sure that you understand, if you're working in this area, in a particular area, that success rate might be 50% here for drilling, or in this other area it might be really tricky and it's only 30%, or this area might be more like 80%. So that kind of information, and that's what we try and do with some of the maps we're doing now, that kind of information can then help budget these projects properly and make sure that you're not putting unrealistic expectations on success rates.
You've done a lot of work on hand pumps, and I mean, oftentimes we hear, NGO and non-governmental organizations or other groups, who fund these projects, and then they let them, they don't stay on top of it, or there's no operational or maintenance funding or things like that. There's capital to install them. So what has been your experience trying to figure out, how many of these hand pumps remain operational over time, and what do you think is the solution to trying to improve those, the operational aspects?
Gosh, big questions. and you're right. I've done a lot of work on hand pumps and really, really love working on rural water supply and hand pumps. And I think that's partly because I got the opportunity as a student to go and spend a summer working in Nigeria with an NGO as a physicist at that point, and went and saw a lot of hand pumps there, and that converted me to doing geophysics and then into hydrogeology. So we've been working over the last 5 years or so trying to get a handle on what the true rate of what we call functionality of these hand pumps are. How many are still working? What proportion are still working? And there's a great organisation called the Rural Water Supply Network that's worked on this for decades, and there's figures, of maybe 20 to 30% not working at any one time. But we developed a project with some great partners in Ethiopia, Uganda, and Malawi, where we went out to try and monitor sort of true functionality, which we felt was how many are actually delivering what they're meant to be delivering. Not just is there any water coming out, but is it actually giving the yield it should be, and is it working for most of the year, or is it got any downtime throughout the year? And what we found with that was that actually the average was more like 50% or less than 50% of hand pumps were actually giving the kind of yield they should have been for a community. So to us that was pretty disappointing, and we thought, well, this is a big issue, and it means that the people that are relying on this service, on this water, are not getting what they need. So we then split the project into sort of two aspects of it. One was then to try and work out what the impacts of not having a functioning water supply were on communities, and there's some great social scientists working on that. And another part where we then deconstructed 150 water points, rural hand pumps, to try and work out why aren't they working? What is it about these that means they only work for 6 months of the year, or they don't give enough yield, or just break down altogether. So that was a big effort with a lot of partners. I think it was 20-person years of field work for deconstructing these pumps and taking them apart and doing lots of little tests on them.
And so do you think then that it's really important for these NGOs and USAID and the World Bank to not just install these things and be at the upfront costs and stuff, but also consider operational aspects? And I think USAID is moving in this direction, and I presume other agencies are also understanding that they need to continue to interact with the communities and I guess get the governance. It's great that you were working with social scientists, because governance is a huge aspect of these things.
Yeah. So what has been really good is that an awful lot of people are now working on this, and you're right, USAID and a lot of NGOs and governments are really focused now on not just installing infrastructure, but trying to make sure that it's about a water service that continues well into the future. And of course, it's not easy. If the answer was easy, it would have been sorted decades ago. But the answer is really complicated, and also it's quite specific to different, or context specific, really. So what we had found in our sort of deconstructing of the water points and also with some social scientists, let's say, working on the impacts, but then we also had social scientists working on the management structures in each of these villages. What we found was that on the physical side, quite a few of these boreholes actually had been drilled in places where the aquifer couldn't support even a hand pump. So the driller had drilled, there was some water there, but the transmissivities we'd say as hydrogeologists wasn't enough to support the yield. So the borehole was always doomed to start off with. It was always struggling. We also found some others where strangely the intake to the pump was just at the water table. So it wasn't deep enough. And you think, well, why didn't they put it deeper? But by taking it apart, we realized it's because the rising main, so the pipes inside had become corroded and there wasn't enough money to replace them. So they just had to chuck out the corroded ones. And this was getting shorter and shorter. So that's something you think, well, that should be able to be sorted. And sometimes the borehole hadn't been constructed just right. So when you drill a borehole, you put pipes inside it, which then have holes in them to let the water in. For some of them, the holes were too deep, and some of the others were too shallow, so they weren't actually next to the bits in the aquifer that were going that had the water in them. So the answers to that are really trying to, I suppose, increase the professionalism of drilling these boreholes, making sure there's enough resources, enough funding to make sure that these boreholes are put in the right place and that they've got the right expertise to install them properly. But then for the long-term functioning of it, it's about getting spare parts of good quality. So sometimes spare parts come in and they're not galvanized properly, so they begin to corrode quickly. So it's about spare parts. In others, it was about the sort of management of these water pumps. And what we found, or the social scientists found, was there was a plethora, that's the right word, of different community management arrangements that people had. Some people maybe a women's institute, and others it might be a church or a mosque or a farming sort of community that would gather funds. The kind of water management committee that's always set up by the NGOs, a lot of the time that wasn't really working. It was just up there in name, and it was really these other institutes that managed the water resources. So the common denominator in it all was having enough funds and having good external support to manage that water resources. I think the whole idea of community management, which people started working on in the 1980s, sounded fantastic and was a fantastic idea if communities could manage these things themselves. But actually, over the years, realized that people need support. I mean, I don't know how to manage my water supply. People do need support and the right expertise, be it from the private sector, be it from the local government, be it from an NGO. People still need that external support to make sure that these water supplies are being properly maintained, and then when they break down, being fixed really quickly.
Right, and so there's a lot of interest these days on solar pumps, and also concerns that with all of these solar pumps that maybe they would not manage the aquifers sustainably. So one group of people think that we have underdeveloped groundwater resources in Africa, and that it's criminal that it's not more developed to help with poverty alleviation and economic development. And others think that you don't want to develop resources more unsustainably. So what are your thoughts about some of these discussions, and what impact do you think solar pumps might have in the future? I think the World Bank has discussions about installing, replacing hand pumps with solar pumps, and 400 in different countries and stuff, 400, 600, that sort of thing. I would like to hear what you think about some of those issues.
Yeah, it again, a really interesting question and an interesting debate. And I can understand why people are cautious about overexploiting groundwater. I think that comes from what might have happened in parts of Asia and India, what's happened in parts of the US and other parts of the world where groundwater has been overexploited. Uh, but I remember a quote from Jude Cobbing, who's somebody who wrote a paper recently about trying to unlock the potential groundwater in Africa, and he sort of said that there's many African countries who'd love the opportunity to manage an overexploited aquifer. Just there hasn't been the resources in there to develop groundwater. So I sometimes think of it as almost a tale of two groundwaters. You've got the groundwater, the overexploited systems that we have in Asia, maybe parts of North Africa and the Middle East. And then in many parts of sub-Saharan Africa, it's of underdevelopment of groundwater. There's so much more potential there. Just excuse me.
Yeah. And do you think, if they start putting solar pumps in and that maybe that will increase development and your background to understanding hand pumps, how do you think they will be able to manage solar pumps, or do you think that will be even more challenging, and which groups might be able to deal with it?
Well, I think that would be my main concern for Africa, or the African countries I've worked in and the communities I've worked with, is that they've struggled to manage a hand pump because of the costs involved and getting the spare parts and the external support. So if you're going to step up to have a solar systems, then need to make sure we've got that even better support in place to make sure that the lifetime costs are put in place. And it's not just constructed and then 3 years' time, the solar panels have been stolen and there's no way back for the solar pump. So I'd be more concerned about that at the moment than an overexploitation of water resources. I also think that because of the crystalline basement aquifer, it's got low permeability. A lot of these, you've got to get the right size of solar pump in there. If you design a scheme and put in a big solar pump, it's unlikely to work well in a crystalline basement aquifer because it will just cut out because the water levels will draw down quickly, and then they will cut out. And we've been working with some electrical engineers looking at this in different projects in several countries. So, but you've got to design these solar pumps to match the groundwater environment so that these boreholes can work well. And you've got to make sure you put in the support to make sure that they're managed appropriately and that the funds are there to do that.
Right. So one huge outcome from your 2012 paper and all the publicity that came with it was funding to do research in Africa, and then developing the network of people in Africa and training people in capacity development. Maybe you can describe the UpGrow project and then the different parts of it, and then how that helped facilitate that development.
Yeah, that was one of the best things that came out of that paper, which and all the media circus that went along with it, was that we then managed to help get some funding for a 7-year program of research into groundwater in Africa. It was called UpGrow, Unlocking the Potential of Groundwater Resources in Africa. And as part of this program, we were then able to do work with a lot more scientists across Africa. So I think we had 150 scientists altogether working across 5 large projects and about 12 catalyst projects, and then something alongside that, which was about making data more available. So and that was producing an online atlas of groundwater in Africa, which took the maps that we had done and then with hydrogeologists in each African country, developing an online sort of wiki summary of groundwater resources for their country. So some excellent research was done as part of the UpGrow program, and it was just really great to have decent funding to fund our partners in Addis Ababa University or University of Makerere or wherever. It was just great to have this jointly conceived projects and jointly funded projects. The bit of work I just discussed about hand pump functionality was one of these projects called Hidden Crisis. There was another one called Grow Futures, which was trying to look at how groundwater could be used for agriculture, to improve agriculture. And that was looking again with social scientists and with physical scientists, looking at how where there's most potential for irrigation to help support livelihoods and where groundwater could help with that. Some other research that was done as part of UpGrow was helping develop a new sensor for measuring whether groundwater was contaminated or not. This is one that it really excites me because it was trying to get us a way of going to a borehole and just taking one measurement to see whether there was bacteria in it or not. So normally, to see if something's contaminated, you take a sample and it's got to be very clean and tidy, and you go and incubate it, and then you need to have a microscope to count all the different cultures and stuff. But this was work where they tried to use something called fluorescence, which happens with organic material if you hit it with UV light. Trying to match that to bacteriological contamination. And through UpGrow, they've got really, really far with that technology now, and more or less just demonstrated that this technique will work, that you could maybe go to a site and see if it's vulnerable to contamination from bacteria or not, just from that. There was lots of other work on viruses as well, different viruses in groundwater, and a great project run out of Oxford University looking at different models for managing rural water supply. So I was talking about, external support being so important. Well, this project then looked at different models, and particularly the private sector, and how that could really help make water supply more sustainable.
It's interesting, Alan, you've been working in all of these developing countries, and, these are semi-arid regions and very low water availability. But you live in Edinburgh, and we never think, because it never stops raining I'm from Ireland originally, and so, we think that drought is something that happens elsewhere and stuff. But even in Edinburgh, I think you also do some work in the UK, and when you have a month without rain or things like that, you have issues with water supply, right? Or
yeah, that's right. Water supply issues are even hitting Scotland, which most people around the world think is so wet. But yeah, in the UK, groundwater makes up about 30% of the public water supply. And this year, we've had quite a bad drought over the summer. It's been very dry over the summer, and a lot of our surface water reservoirs have been running low. There's hose pipe bans and such like. So just in the same way as for Africa, where people are developing groundwater as a more resilient water resource, it's the same issue here. Is that for water companies trying to think of how to develop groundwater as a more resilient water supply. And for Scotland, we have quite a lot of little private water supplies, little wells and springs, and they're tapping very shallow groundwater. Some might argue, is it groundwater or not? You could have a theoretical debate with a hydrologist and a hydrogeologist, maybe only four meters deep. So a lot of them do get quite vulnerable. If it stops raining for 2 or 3 months, they get quite vulnerable. So yeah, there's a lot of thinking here. How do we improve the resilience of water supply for these private water supplies if we have, which would be unheard of, if it stopped raining for 3 months in Scotland, what would happen to these water supplies? So lots of thinking going on.
Right. And so, you've received a lot of funding in the past from agencies in the UK and elsewhere. How is the funding situation these days? I mean, DFID, has changed, or, how has that evolved, and what do you see the future for funding work in developing countries?
Yeah, well, funding has not been great over the last few years. So, like several other countries, the UK has reduced the amount of money it goes towards international aid as a result of the money sent out for COVID. So the amount of money for research into international issues such as this and for aid has reduced significantly. So it's not so easy to get funding now through that sort of route. So it's been, I think it's challenging for everybody over the world at the moment to get funding, which is a shame because the not just for us, but I think it's a network of scientists that you put together. So this Upgrow program we talked about, 150 scientists developed some great research capacities. There's fantastic young early career researchers in different countries coming through, and it would just be good to have funding opportunities for them to carry on research that's meaningful for them and their country, and to make sure that that's then going into practice. There is quite a lot of money going into some sort of capital projects at the moment. So maybe 100 million here and there for developing water supply. And what we'd like to make sure is as part of these capital projects, some money is then put towards actually understanding the groundwater resources and doing that kind of legwork behind the scenes to make sure that these water supplies are put in place and don't dry up really quickly.
So we've talked about a lot of different things, Alan, and I'm a huge admirer of your work and your group. Is there anything else that you would like to add, or that we've missed in discussing these topics, or?
I don't think so. I think we've ranged all over the world. I mean, I might not have said it throughout the different topics that we've covered, but of course, all this work has been done with loads and loads of other people. So I've been really fortunate to have worked with some great people, not just at BGS, but also in all these different countries that I work in, and just how great a lot of our sort of collaborators are in these different countries. And I think looking forward, we just need to keep working on groundwater because it is the resilient water resource for the future, and it's been such a blessing to so many people where surface water is in short supply or is variable, and we need to protect these water resources. We need to understand them and protect them so that future generations can really benefit from them as well.
I think we've seen that with Cape Town issues, where they were totally dependent on the surface reservoirs, and then they were moving towards day zero, and then they started trying to develop some of the groundwater resources. I think you knew some of the people involved in that, right?
Yeah, heard some great stories there, and how they very quickly realised that they need to drill some groundwater or exploit the groundwater resources through some wells, and they quickly tried to put in water supplies at key places such as schools and hospitals and such like. So yeah, it was a great visual aid of how important groundwater resources can be, and when these droughts hit. Yeah.
Well, I really appreciate you taking the time to chat with us today, and I wish you luck in all your future work and heading up the hydrogeology group at BGS and everything, and look forward to collaborating with you more in the future. Thank you so much, Alan.
A pleasure. Thanks a lot, Bridget.